Welcome back. You've hung with me so far in eliminating angle parameters. There are a couple of examples on page 5 of the parametric packet where I think it would be good to practice our skills with the types of problems we just went over. I would say, here's a suggestion, go back to number 3 when you have some time, test yourself out. See if you can solve it just like we did number 1 on the other side, and if you can get the graph of a conic section and use the parametric equations to get its orientation. We're going to do this out of order. We're going to come back to 4. I'll circle that one too. And I'm going to actually, in the next section, I'm going to add a number 6. So I'm just going to leave this space untouched because 5 is a pretty quick starter for this portion of the video. And I just gave myself a new set of axes on which to graph. Can you try 5 like we did the first one on the other side? You're trying to relate sine and cosine. So step 1, solve for the trig functions. This one doesn't look too bad. Cosine of theta equals x over 2. And notice the same coefficient here. Sine of theta equals y over 2. It doesn't matter which one you put first or second. Sine squared plus cosine squared still always equals 1. So square them both, add them up, set them equal to 1. So I'll square the cosine, x squared over 2 squared. I'll square the sine, y squared over 2 squared, so and a plus in between, equals 1. This is from your Pythagorean identity that, and I did it out of order, cosine squared of theta plus sine squared of theta equals 1, always. Does that look like an ellipse to you? Could you be more specific than that? It's an ellipse with the same A and B. It's a circle. So in this case, because of those original 2's matching up as coefficients, your standard form equation of a circle can be multiplied through by 4. And what could be better? You're going to graph the cutest little circle that has radius squared of 4, so 2 units in each direction. Now, please don't laugh as I graph a pretty ugly circle. Hopefully yours looks a bit better than that. You don't have any domain and range problems. Your domain and range of your original is -2 to 2, as is this graph. So nothing to alter about the domain or range of this rectangular equation, but you are always required to put orientation onto a parametric graph. So plug in some values in your head, some quick quadrantals, like theta equals 0. When theta is 0, you get 2 times the cosine of 0, which is going to be 2 times 1. And I'll list this out just to organize it. When theta is 0, x equals 2 times 1. Y is going to equal 2 times the sine of 0. So 2 times 0 gives you this first vertex at 2, 0. Here's your point at theta equals 0. How about pick another value above 0? It doesn't matter which. I'll pick the next quadrantal, pi over 2. So 2 times the cosine of pi over 2, 2 times 0 gives you 0. And 2 times the sine of pi over 2, 2 times 1 gives you this next vertex. Here you are at theta equals pi. No, I don't want to switch colors. At theta equals pi over 2. And we can just put arrows in this one going clockwise, right? We'll go clockwise for that graph. Now, we're going to backtrack. So leave the space here for us to come back to it at a later date. The last one I wanted to look at is number 4 for some more good practice, especially with domain and range restrictions of a tangent and secant example. Let's do it. All right, step 1, solve each of these for the respective trig function. So tangent of theta equals x minus 1. And here secant of theta is going to equal y minus 2 over 2. Check that out. Make sure it looks good. And we can use the Pythagorean identity that's secant squared. I'll list it here. Secant squared of theta minus tangent squared of theta always equals 1. We want to plug in rectangularly in terms of x and y. So y minus 2 over 2 squared minus, how about the tangent, x minus 1 squared has to equal 1. And you've got this thing squared out, so standard form y minus 2 squared over 4 minus x minus 1 squared over 1 equals 1. Okay, so you have a hyperbola, and we can get some features of it in a second. Mainly the center, the vertices, and the asymptotes. Feel free to pause and find those on your own before you check them with mine. Center comes from the numerators, right? It'll be 1, 2. Vertices, use your A value. Go up and down because this goes with the Y's 2 units. So you're at 1, 2 plus 2 and 1, 2 minus 2, 1, 0. And we'll talk about domain and range restrictions because we might not be needing both of those vertices. Asymptotes are good for the shape of this graph. I want to spell that correctly. use point slope form with them going through the center. So y minus the y coordinate of the center equals plus or minus, I'll skip the slope for a second, x minus the x coordinate of the center. You know your slope for asymptotes for a hyperbola is either a over b or b over a. In the case of a vertically oriented ellipse, you're rising a and running b. So it's going to be a over b, which would be 2 over 1, and we can just call that 2, plus or minus 2. Like this. Now, I wonder if this one's like the last one where we're only graphing either the top branch or the bottom branch of that hyperbola. We got to go back to the original parametric equation to make that decision. And sometimes it's good to just do this off the bat. I don't think our domain is restricted whatsoever. Tangent of theta could be any value under the sun. So x, fancy symbol here, x just belongs to the real numbers. X can be anything, no need to restrict. The range here is what's going to get restricted. If you're strictly staying between pi over 2, so 0, 1, pi, the other quadrantal is -1, 0, and it gets down to 0, -1. Think of what secant is going to become, right? Secant is flipping the x value. This is the lowest the x value ever gets to, leaving negative decimals in the other two quadrants. So the highest secant is ever going to get to is going to be -1. So secant of theta is going to stay less than or equal to -1, just like in the last problem in number 2 from the other page, which means y is going to stay less than or equal to, we'll say 2 plus 2 times -1. So 2 minus 2, y needs to stay less than or equal to 0 here. We will put that domain restriction on our rectangular equation. So y is less than or equal to 0. And there actually isn't quite enough room to put the center on here. There is enough room for the vertex, but we just want the bottom half of it. We don't want this graph to come up above that vertex. So 1, 0 is a vertex. And then up from if you did want to put the center on there, that would be at 1, 2. The center's up here, extended a little bit. We could throw the asymptotes on there quickly, just use the equation that's at the bottom. So they go through the center and their slopes are plus or minus 2. Your rise over run is just going to be 2 units here. And I apologize for this rough sketch, but that's what it is, just a rough sketch. We want a slope of 2 here. Come on, don't fail me now. So, wish I could do a little better than that. You just want, like we mentioned, the bottom branch of this hyperbola. So curve it up, have it touch the vertex, and come down the other way. A couple points plugged in can help you get the orientation. We only want to use values, again, that are within the original kind of expressed domain of the function. So we just want to stay with theta being between pi over 2 and 3 pi over 2. Some values won't give you any defined value back. If I try to get an x value here, 1 plus the tangent of pi over 2, tangent of pi over 2 is undefined, right? Y over x. So we'll say for this one, not going to give you a point. Pick another value. Pick a quadrant 2 value. I chose 3 pi over 4. Either use your exact values or use a rounded decimal, that's fine. But if you go 1 plus tangent of 3 pi over 4, that's 1 plus -1 gives you 0. 2 plus 2 times the secant of pi over 4, here's the exact value. 2 minus 2 square root of 2. And then let's pick one more. I don't think that 3 pi over 2 is going to give me a defined value, so I just chose another random value. I chose pi. And pi plugged in here, 1 plus the tangent of pi, 1 plus 0 gives you 1. And then plugging pi into this y expression, 2 plus 2 times the secant of pi is like saying 2 plus 2 times -1, 2 minus 2 gives me 0. So what that means is this orientation, it's going to be you have a dot at 0, negative, or 2 minus 2 square root of 2. That's that y-intercept of the blue graph here. And then as you're traveling up in the thetas, you're actually going to the right on the curve, because then that takes you to the vertex. So squeeze in a couple arrows of orientation here that should be going this way, up and then down the curve to the right. All right, excellent work today. Stay parametric. I will talk to you soon.